Alright, let's just dive straight into this explainer. Today, we are tackling a massive mistake that even top-tier IGCSE students make when visualizing computer data. Picture this. You sit down for your Paper 1 exam, you write down that a computer stores ones and zeros, and you confidently think you've secured the mark. But you haven't. Actually, you've just stepped right into a classic examiner trap.
Now honestly, do you think little numbers are physically zooming through your CPU? Because if you do, you're falling into a major conceptual trap. It's a super common psychological block, really. We talk about binaries so much that we start believing these digits are literal things bouncing around the motherboard. But to truly master Cambridge computer science, we have to look past the numbers.
Here's the fascinating truth. Binary is just our human translation of pure electrical states. As the syllabus resources clearly point out, a computer is, at its core, an electronic machine. It doesn't read numbers at all. It reads voltage. The ones and zeros are simply a human abbreviation for an electrical circuit being on or off. That's the whole shebang.
So think about what this actually means. All data, facts, figures, text, images, absolutely everything must be converted into these two states to be processed. This is what binary is. Any system that exists in exactly two different states, and only two, is a binary system. Think of a simple flashlight, right? It's either on or it's off. There is literally no in-between. To a computer, everything has to be broken down into these fundamental states.
Okay, to see how we build this up into complex data, we need a bit of a mathematical framework. I'll share an examiner clue with you in a few minutes that relies entirely on understanding this grouping. A single 1 or 0 is called a bit, which is just short for binary digit. But computers, they don't usually deal with single bits one at a time. Instead, they bundle them up into groups of 8. And that group of 8 bits, that's what we call a byte. Now, why does 8 matter? Well, with 8 of these tiny on-off switches in a single byte, the maximum combination of values you can represent is the decimary number 255, counting from 0. By combining several bytes together, the computer can store significantly bigger integers. But wait, what if the data isn't a neat whole number?
You know, if you're wondering about decimals, the computer does something incredibly clever. It dedicates a whole extra byte of data specifically to store the position of the decimal point. It's a brilliant piece of engineering, honestly. Just like in our standard denary system where we use a decimal point, say 0.25 for a quarter, the computer uses a similar approach. It dedicates specific storage just to tell the system exactly where that point belongs among the bits.
All right, let's shift gears and compare some formats. Text characters use coding systems like Unicode, while images require a completely different method. It's fascinating because both ultimately end up as electrical signals, but the translation process is totally distinct. For text, the computer basically uses a massive lookup table called Unicode, where every single letter or symbol gets assigned a specific digital number. But an image, there's no alphabet for a sunset, right? So for bitmap graphics, the file literally stores the exact position and color of millions of tiny dots. A computer image is just a massive grid of pixels, and each of those pixels, each tiny point of light on your screen, has its specific color code stored as, you guessed it, a binary number. So millions of pixels means millions of bytes of binary data. Okay, let's zoom in even further. We have all this stored data, but honestly, there's no point in having millions of ones and zeros just sitting there in memory doing nothing. A computer's entire job is to process that data into useful information, and the absolute command center for this operation is the CPU. The Central Processing Unit, or CPU, is the absolute core of the whole operation. It utilizes logic gates to manipulate all those electrical signals we've been talking about. Remember the definition we established earlier? A computer is an electronic machine for processing data. Well, the CPU is where that action physically happens. It pulls the data from the main memory and just gets right to work.
Breaking it down, the ALU handles logic and math, the control unit manages the flow of data, and the bus provides the short communication links joining them all together. Think of the control unit as a traffic director, making sure data moves precisely where it needs to go. The bus acts as the highways connecting the different parts of the processor. And the ALU, that's the heavy lifter where the actual math happens. And all of these components work together in what's essentially the heartbeat of the processor. It's constantly pulling instructions and acting upon them in a continuous, unbreakable loop. The CPU fetches data from the memory, figures out what to do with it, and then executes that instruction. Fetch, execute, fetch, execute. This happens billions of times every single second. It's wild.
So, what does this all mean for you?
Remember that examiner clue I promised you earlier? It all comes down to using Cambridge-safe terminology instead of generic guesses. Understanding how a CPU processes binary is fantastic, but if you can't articulate it according to the strict expectations of the mark scheme, you are leaving easy points on the table. Let's look at exactly how to secure those marks.
Let me tell you, generic definitions score poorly. However, an answer that directly references the scenario-specific data types secures maximum marks. For example, if a question asks how an automated greenhouse sensor system processes data, you don't just write, "It uses binary." No way! You must state that the analog temperature data from the sensor is converted into digital binary data so the CPU can process it. You absolutely must use the nouns from the specific scenario to hit the nail on the head.
Oh, and here is a classic trap. Validation versus verification. You should always use validation when testing if data makes sense and verification when checking if entered data accurately matches the source. Examiners see this mistake constantly. Validation is asking, is this data reasonable? Like checking if a person's age is between 0 and 120. Verification is asking, did it copy over correctly? Like typing your password in twice to ensure it matches. Do not mix these up. Seriously.
So the absolute crucial point here is to follow a strict 4-step framework in your exams to guarantee you hit every required mark scheme point without rambling. First, define the term precisely. Second, explain the mechanism of how it works. Third, apply it directly to the scenario given in the prompt. And finally, state the consequence or advantage. This sequence literally forces you to think like an examiner.
Okay, let's do a quick knowledge check. Mentally lock in your answer right now based on what we just covered. I want you to actively retrieve this. We talked about the control unit, the bus, and one other specific piece of hardware. Which one actually runs the electrical signals through logic gates using the strict rules of arithmetic?
If you guessed the ALU, or arithmetic and logic unit, excellent job. It passes data right through those logic circuits using the strict rules of logic and arithmetic. It is the absolute powerhouse of the CPU. By combining millions of microscopic on-off switches into complex logic gates, the ALU is what ultimately transforms raw binary inputs into the processed information we rely on every single day.
Now, to make sure you keep upgrading your knowledge, the creators of this source material highly recommend subscribing to their channel, Ace the Exams, to excel in your Cambridge examinations. As they point out, the mark schemes are undeniably strict, but with structured strategies like the ones we've covered, you can absolutely master them.
But wait, you've got the framework now, sure, but what actually happens when this perfectly formatted binary data encounters the absolute most dangerous question types on paper 1? To see how this theory breaks down under the intense pressure of a complex data analysis scenario, you absolutely must jump into our next explainer. Let's find out together.